So yesterday we looked at solving exponential equations by creating an equation that had a common base on both sides. What that meant is that you were able to write the equation as a base raised to an exponent equals to the same base raised to an exponent. So, well, let's just tackle D, which is maybe one of the more complicated ones here. 16 and 32 are both powers of 2. 16 is 2 raised to the 4. 32 is 2 raised to the 5. Now, how do you know that? Well, you have a calculator, right? You have to explore this on your calculator, and sooner or later, these numbers will become more and more familiar to you. That means that for this equation, I can rewrite this as 2 raised to the 4 raised to the 2k minus 3. And this is equal to 2 raised to the 5 raised to the k plus 3. Our laws of exponents say that a power of a power, which is what we call 2 to the 4 to the 2k minus 3, that a power of a power can be simplified by multiplying the exponents. So this equation now becomes, on the left-hand side, 2 raised to the product of 4 and 2k minus 3, and on the right-hand side, 2 raised to the product of 5 and k plus 3. Since the bases are the same, since these two bases are the same, and both sides are equal, what that means is that these two exponents must be the same. And really what we're into here is a territory where solving this equation, 4 times 2k minus 3 equals 5 times k plus 3 is fairly straightforward. You know, it's not even a Math 30 problem at this point. You expand this out and get 8k minus 12 equals 5k plus 15. As simple as this is very often where students will make mistakes. Because it's so simple, you just put your brain on autopilot and start writing without even thinking. So make sure you double check things. 8k minus 12 equals 5k plus 15. Subtract 5k from both sides to get 3k. Add 12 to both sides to get 27. K is equal to 27 over 3, which is 9. In this set of practice problems, there were also problems dealing with applications of exponential growth and decay using that formula that we've kind of talked about for a couple of days now. So do me a favor. Are there any questions anybody would like me to go over? So number 11. Now I believe, I could be mistaken, but I believe the answer to question 11A in the back of your textbook is incorrect. And you may have a textbook where somebody has crossed out that answer for 11A. The same goes with 13. They have for 11A that the amount of money, what we would call Y, is equal to 1,000 times 1.02 raised to the end. Now let me go through number 11 and show you why that answer is wrong. Number 11 says you invest $1,000. Okay, so first of all, the initial amount of money is $1,000. When we're talking about this formula, Maddie, A is the initial amount, so A is 1,000. No problem. It's 8% per year compounded quarterly. This happens to match the exact situation we had with, I think, Elaine's investment in our examples yesterday. You understand why if it's 8% per year, but it's cut into 4 quarters, you only get 2% at a time. This is a really important idea that I'm going to have problems with my computer today. We'll just wait for it to catch up. That year, that per annum or per year is 8%. And I'm just stalling here while I hope my computer catches up. That's 8% for the whole year. So if that rectangle represents a year, and Wayman, when you come in, can you try to be here on time, please, and just come in around the back of the room. That 8%, Maddie and everybody, is cut into 4 chunks. So if you take 8% divided by 4, you're only getting 2% every time. And what that leads us to is that B is 1.02. And I'm not going to write it out, but what you would do on a written response is say it's 100% plus the 2%, which is 102%. You might have to, on a written response, explain this, but I think this graphic goes a long way to explaining what's going on. And P is, and you have to remember these things, P is the length of time it takes to get interest. So if this whole rectangle is a year, then this is 0.25 of a year, this is 0.25 of a year, etc. So P is 0.25. And I would, well, I don't recommend. I just prefer working in years. Some people will want to put 3 months there, but I just like years. Okay. So when we put this together for A, you're going to get Y equals A, 1,000. This is for question A. A is 1,000 in the formula times 1.02 raised to the T over 0.25. And that's why I've told you here that the answer that they give is just wrong. I think you would be okay then solving B and C. And I don't know if I assigned 13 as well, but 13 suffers from the same problem in the textbook, that the authors just, they know what they're doing. They just made a little mistake, you know, which we all do. Any other questions from yesterday's work? Okay, what we're going to do is get started with the next lesson. And again, as I said, there's no rush here. We will easily get through this lesson. It's not a monstrous lesson time-wise, but it's a monstrous kind of lesson concept-wise. And I had mentioned to the class many times that, you know, students struggle with the 2 trig units, but this is also a unit that some students really, really struggle with. And if we can get a really good foundation for this today, then when we look at further applications and uses for logarithms, you'll be better off. So today, this is section 8.1. It's called Understanding Logarithms. It's on page 10 of your unit handout. We're going to be doing a number of things. We have to start off the lesson by comparing exponential functions and logarithmic functions, because really, I'll explain it to you this way. If you want to know what a logarithmic function looks like, you have to look at a corresponding exponential function and do something to it. There's a really intricate connection between exponents and logarithms. And at some point, I'm going to tell you that really all a logarithm is an exponent. This next point is very, well, I want to go back here, and I have to get something running on my computer. I've lost a program. Just give me 1 second. I want to make a distinction here between the first objective, the first bullet that you're looking at on the screen, and the second one. We'll get to the third one in a second. So this first bullet is talking about two, man. is talking about two different things. This is really important. You guys need to focus on this. It's talking about an exponential function and a logarithmic function which are different things. They're two different things that we can compare. The second bullet, and I'm going to cross my fingers as I pick another highlighter. The second bullet is talking about the same thing written differently. So an exponential function and a logarithmic function are different things, but I can take an expression and translate it into a different form. And this is kind of like this one that I've highlighted in green is kind of like saying if you have a logarithmic expression, you are allowed to rewrite it as an exponential expression, but it means the same thing. It's like translating the word hello to bonjour, or bonjour to hello. Okay? And then we're going to be evaluating logarithmic expressions. So let's get started here with this. What is a logarithmic function? What a logarithmic function is an inverse of an exponential function. So we've learned about exponential functions, and we've learned about inverses of functions. We learned about inverses of functions in the very first unit. And I'll remind you here that the procedure for finding an inverse of an equation or of a relation or of a function involves taking the x in the equation or relation or function and the y and switching their positions. So, as an illustration here, if you take a look at this, we can call it an equation, you can call it a relation, you can call it a function, it doesn't really matter. That's not my point here. This is a linear equation, which if you graphed, you know you would get a line with a slope of 2 and a y-intercept of -6. And if I said to you back in Unit 1, what is the inverse? You would say that the inverse is x equals 2y minus 6. Remember that? You just switch the x and y. So these are inverses of each other. These are different things. They're not the same. They're different. The only thing is, when we have a relation between x and y, we like to rearrange the relation for y. And this is a fairly easy one to rearrange for y. We can add 6 to both sides and get 2y equals x minus x plus 6 and divide everything by 2, so you get that. And I want everybody just to mull over in your head, which means think about how you would get y equals 1/2 x plus 3 from x equals 2y minus 6. You'd rearrange it, right? And you know how to rearrange it. Another example would be y equals x squared and x equals y squared. Now this is not in your notes, but it's going to illustrate a very important idea here. And again, I can see that some of you are not really focused right now. Please try to focus on what I'm talking about. Y equals x squared and x equals y squared are inverses because we've switched x and y. But if I gave you x equals y squared and I said rearrange it for y, if you were a grade 9 student or even a grade 10 student, you don't know how to do that. You really don't. It's not just taking the square root, because in grade 11 we learn that when you rearrange that for y, it involves this plus or minus concept. And that plus or minus concept was new to you last year. So prior to last year, or last semester for some of you, if I said rearrange x equals y squared, you'd just shrug and go, I don't know how to do it. I haven't been taught how to write it rearranged for y. Keep that in mind. You don't know right now how to rearrange any equation. You don't. You're being taught how to rearrange certain equations a step at a time. So let's get back to, and by the way, they're called a quadratic function and a square root function. Let's get back to this topic, that a logarithmic function, it says at the top of your page there in bold, a logarithmic function is the inverse of an exponential function. So let's look at the exponential function y equals 2 to the x. This is on page 10 its inverse is called the logarithmic function, because a logarithmic function is the inverse of an exponential function. And it's shown below. Just look at this. I've told you that an exponential function, is the inverse of a logarithmic function. You know that this is an exponential function because we've taught you that in the first lesson of this unit. And you know that the inverse is found by swapping x and y. So this should be no real surprise, what I have here. This should make sense to you. Am I right here? Okay. And I'm going to explain this before I show you what I have in your notes. We don't want x equals. We want to write that as y equals. Now again, these two things are different. They're not the same thing. They are different. But what we want to do is rewrite that one that's highlighted in green as y. And I want to go back over here to this. I want to impress on you, which way did I go here, that this is an original function. This is the inverse, but this is the same as x equals y squared. Are you with me? That the function on the left is a function. What I have on the right is different than it because it's the inverse, but what I have written below the inverse is the same as what's above. This goes to what I was talking about at the beginning of the lesson. That you can translate x equals y squared to y equals plus or minus root x. Okay? Y equals x squared is not being translated to x equals y squared. By translated, I mean converted. It's being changed. So, I also mentioned to you that prior to last year, you didn't know how to rearrange for y x equals y squared. Well, right now, as it stands, if I say to you rearrange this highlighted green function for y, you have no clue how to do it. There is no way to do it. And I'm getting a little bit into the philosophy of language and mathematics here, but this thing here, this plus or minus the square root is just an invented symbol that means the inverse of squaring y. That's all it means. Well, keep that in mind now as we move forward. Normally you want to rearrange that for y, but you can't rearrange x equals 2 to the y for y. Instead, we invent a way to write it, just like we invent plus or minus the square root. And we write it as this thing. So, in keeping with my theme of highlighting, that logarithmic function, which I've highlighted in green, can be written this way. We can write x equals 2 to the y as that thing, and that thing is pronounced, there's a number of ways to say it, and you'll get used to this. That thing is pronounced y equals log base 2 of x. It would be kind of the analog to plus or minus the square root of x. Or it can be pronounced y equals the base 2 logarithm of x. So these two things are the same. When you look at the top of your handout, can I just borrow your handout for a second? When you look at the top of your handout, there's a graphic with two boxes. I guess I'll just show it to you up here. There's a graphic at the top of your handout with two boxes here, and these things are different. They're related, but they're different. This box is showing you two things that mean the exact same thing. And you have to be able to translate from one to the other. And it doesn't matter whether it's x and y and 2 or any other numbers or letters, and we'll get to that in a bit. So, in general, and we're going to have to talk about what this means, f of x equals log base c of x is a logarithmic function, and it's the inverse of the exponential function g of x equals c to the x. Ignore all of that stuff in the second line that you're looking at up here. I'm telling you that y equals log base c of x and y equals c raised to the x are inverses. Why are these things inverses? Well, I want to run through this with you again, and I know this gets repetitive. But again, you need to focus. Give me 1 second here. Why are they inverses of each other? Because if I said to you, take this y equals c to the x and write the inverse is found by switching x and y. Correct? How do you rearrange, how do you rearrange that equation that I've just written, x equals c to the y for y? You write it as y equals log base c of x. There's a lot going on here. You will get used to it, but it's going to take a lot of thought and practice. What am I talking about here for this? Well, I'm going to start off with that. C is greater than 0 and C is not equal to, oh boy, do you have C is not equal to 1 on your handout? Good. When I retyped this, I made a mistake. This is C is not equal to 1. This is that same thing that we've talked about before with exponential functions. Remember, I've given you that graphic where C is not equal to 0, not equal to 1, but it can be between 0 and 1, and it can be greater than 1. You know what I'm referring to, I hope. Well, since C is the base of the exponential function, then C is still a base of some type of an exponential function when you take the inverse to get the logarithmic. So C still has those properties. I'm not going to talk right now about why x has to be greater than 0. I just want to tell you right now that you're not allowed to take the logarithm of a negative number or of 0. And just to demonstrate that to you, you have a calculator and you have a log key. Don't worry about exactly what that log key does, but it is a logarithm key. If I take the logarithm of 50, I get some number, okay? Don't worry about what that is just yet. We'll get there. If I take the logarithm of 1, I get some number. If I take the logarithm of 0.579, I get some number. Don't worry about why I'm getting these numbers. But if I try to take the logarithm of a negative number, I get an error. I just want you to focus right now on the fact that the argument of a logarithm can't be negative. And when I didn't try, let's try taking the log of 0. It can't be 0. All right, so as the first part of this, which we covered in the seminar, kind of illustrates, I think, so far this is about language and understanding a process rather than doing any real math. So again, when you take a look at log base c of x and y equals c to the x, those are inverses of each other, because when you take y equals c to the x and find the inverse, you swap out x and y to get x equals c to the y, but we've invented a way to write x equals c to the y as y equals log base c of x. So your textbook uses c for the base, but your formula sheet will use b everywhere. Let's take a look at the first example. It says graph both y equals 2 to the x, and on your printout for some reason I'm missing the second function. It's say and y equals log base 2 of x on the same set of axes, and complete the information in the boxes. So in order for us to graph y equals 2 to the x, we just go back to the first lesson in this unit. We know that y equals 2 to the x will have a horizontal asymptote on the x-axis. We as well know that it has a y-intercept of 1. I've got some weird things going on here. Give me a second to fix a couple of things. That should be okay. We also know that y equals 2 to the x has a y-intercept of 1. Any exponential function of the form y equals c to the x will go through 1 on the y-axis. In addition, we know that since the base is 2, every time we increase x by 1, y gets doubled. So we could make a table of values, or we could just say we go up by 1, we double y. We go up by 1 again, we double y again. We go up by 1 again, we double y again. You know, the bottom line is 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. We run into that. Give me a second to start another Google Meet here. Good morning, Ian. We get into that idea that if I go backwards to -1, the y value will be cut in half. I don't think we want to go any further in the left direction, but we could sketch this now. And I just want to double check. Ian, can you type something in the chat window and let me know that you can hear me? Perfect. Thank you. So we can sketch this. Again, I'm not too concerned about your ability to sketch a smooth curve. It's easier on paper than it is up here, but I'll do my best. We're going to get a curve which looks something like that. Not happy with the wobbliness to that, so I'm going to do it again. Looks something like that. And I don't really have a lot of room here, but I'll put a little arrow on the other end of it. So that is the exponential function y equals 2 to the x. Y equals 2 to the x and y equals log base 2 of x are inverses of each other. And again, it's going to take a while for this to stick, but what is the inverse of y equals 2 to the x? The inverse of y equals 2 to the x is x equals 2 to the y. But how do you write x equals 2 to the y? You write it as y equals log base 2 of x. So if we want to graph the inverse of this, we just have to remember that inverses are found by switching x and y, and that means switching everything about x and y. If the x-axis on one function is a horizontal asymptote, then the y-axis on the inverse will be a vertical asymptote. If the original function has a y-intercept of 1, then the x-intercept of the inverse will be 1. Everything about x and y switch. And if you wanted to, I'm not saying you need to do this, but if you wanted to, you could say to yourself, well, the coordinates of this point on the original function are 0, 1, and inverse is found by flipping those two numbers over. That becomes 1, 0. Well, 1, 0 is that point. And again, I'm not saying populate your graph with all of these weird arrows and ordered pairs. I'm just telling you that we're swapping x and y. So, for example, and I'm going to get rid of this. For example, and this is just me teaching, you don't need to write this down, this is at 3, 8. Well, if I switch 3, 8, it's going to be 8 comma 3. This is at 2 comma 4, and I'm going to erase these ordered pairs. Again, this is just me instructing here. If I switch 2 comma 4, I'm going to get 4 comma 2. This point is negative 1 comma a half. If I switch those, it's going to be a half comma. It's going to be a half comma negative 1. And what we're going to get for the logarithmic function is this general curve. And by the way, I hope that everybody recognizes that these two graphs are reflections in the line y equals x, which they should be because they're inverses. Are you still with me? I feel as though maybe I'm a little off kilter today. Am I going too slow? Am I going too fast? It's Goldilocks then, just right? Okay. So now we need to write out the information for these functions. Well, this first box for the information about the graph of the function y equals 2 to the x is from the first lesson in this unit. This is nothing new. We look at the brown graph, what I've drawn in brown, and we say the equation of the asymptote is the x-axis, which is y equals 0. I'm not using green for any particular color other than that's what I happen to choose. The y-intercept is, rather than just saying 1, let's be a little more informative and say 0 comma 1. There is no x-intercept. The domain is x is any real number, and the range is y is greater than 0. Any questions with those 4 properties of the graph y equals 2 to the x? All right, so if I want the equation of the asymptote for y equals log base 2 of x, I'm now looking at the red graph, but it has an asymptote that's vertical on the y-axis, and the equation of the y-axis is x equals 0. I did not need to look at the graph. If I recognize that these two functions are inverses, then this equation of an asymptote can be used to find this equation of the asymptote by saying an inverse is found by swapping all the properties of x and y. So whatever is true about x becomes true about y and vice versa. Similarly, if I take a look at the y-intercept, the original function has no x-intercepts, which means that there cannot be a y-intercept because x and y switch. And if you take a look at the red graph, it never touches the y-axis. What about the x-intercept of the red graph? Well, the y-intercept of the original graph is at 0 comma 1, which means we're going to have an x-intercept at 1 comma 0. The domain and range. Well, looking at the graph, the red graph, the logarithmic function, the domain is x is greater than 0. The range is y is any real number. But again, look at the domain and range of y equals 2 to the x and compare it to the domain and range of y equals log base 2 of x. The domain description became the description for the range, and the range description became the description for the domain. You still with me? Okay. Tomorrow what we will be looking at is transforming that function, but for the time being we're going to move on and get into the most important part of logarithms, which is understanding what they mean mathematically, not as a graph. So I'm going to come back to this statement. This is at the top of what I believe is page 11. I'm going to come back to this statement over and over and over again. A logarithm is an exponent. Okay? So this sentence in this box is saying two things. If I have y equals c to the x, that's a function that's exponential, I can write it as x equals log base c of y. I'm pointing out to you, I hope, that this and this mean the same thing. It's like we're bilingual mathematically. Y equals c to the x is the same thing as writing log base c of y equals x. On the other hand, if you have y equals log base c of x, which is different, it's a different exponential, or it's a different function, that can be written this way. And what you have to be able to do is sort out, when you translate from one to the other, what goes where. So let me explain to you one way to do it. These are the same thing, okay? Now, I told you that a logarithm is an exponent, okay? This is a logarithm. Okay? That's a logarithm. What is it equal to? It's equal to x. So x is the logarithm. X is the exponent to which you raise the base to get y. The logarithm is always equal to the exponent. So in other words, whatever is by itself in the logarithmic form is the exponent in the exponential form. Similarly, we can use the same kind of rule. Whatever is by itself in the exponential gets eaten up by the operation in the logarithmic. So if I said to you, how can we write y equals log base c of x in exponential form? Y will be the exponent to which you raise c to get x. If I say p equals log base q of r, that means p is the exponent to which you raise q to get r. It's always going to be, in logarithmic form, the base raised to the other side equals what you're taking the logarithm of. And you need to convert them. So for example, if I say duck equals fish to the moose, and I want you to write that in logarithmic form, the first thing you can notice, by the way, is the base is the same no matter which form you write it in. It's the other two quantities that get flipped. So that means that if I say what is duck equals fish to the moose in logarithmic form, it's got to be a log base fish. It's got to be a base fish logarithm. The thing that's by itself right here is duck, and moose is buried inside of the operation, so that's going to switch. Moose will be by itself, and moose is equal to log base fish of duck. It doesn't matter what those things are. You need to be able to rearrange them. And here is why. This is maybe the most important thing today. If you have a math problem in this lesson or further lessons and you don't understand what you're being told, translate it to the other language. If you were given a logarithmic equation and you don't understand it, rewrite it as exponential, and maybe you will. Or vice versa. Okay? So, example 2. This is the meat of this lesson. Convert each of the following from exponential to logarithmic form. So this right now, n equals 4 to the p, is written as an exponential equation. We're going to write it as a base 4 logarithm of something equals something. And that logarithm has to be equal to the exponent to which you raise 4 to get n. So when it's in logarithmic form, and I know I'm going to be very repetitive today, but when an expression is in logarithmic form, the quantity that's by itself is the exponent in exponential form. If I say to you 2 to the negative 5 equals 1/32, then that can be written as a base 2 logarithm of 1 over 32, and it's equal to the exponent to which you raise 2 to get 1 over 32. We okay with A and B? Okay. Log base 10 of 100 equals 2. Okay, so 2, and listen to the language. I'm going to be using this again and again. Hopefully it sticks. 2 then is the exponent to which you raise the base to get what you are taking the logarithm of. Remember, the thing that's by itself in logarithmic form is the exponent. So over here, this would be x raised to the m is equal to k. Did example 2 just have an A and a B? There was no C? There was a C. Four log base b of 9 equals 16. I think that's an important one. I don't know how it got lost. 4 log base b of 9 equals 16. An important lesson with this one is you cannot rewrite this in exponential form unless it's just a single logarithm. Not 4 times the logarithm, not 8 times the logarithm, but a single logarithm. So you have to start by dividing both sides by 4, and then we get log base b of 9 equals 4, because 16 divided by 4 is 4. Rewritten, that becomes b raised to the 4 equals 9. Are we okay with 3c? I guess that was 3c. Okay. Oh. Never mind. Let's take a look at number 4. I thought I missed one on number 2. Number 4, determine the value of each expression. So this is interesting because we don't have an equal sign, but we can make an equal sign, and many of you will not have to rely on doing this all the time. But if we want to know what this is equal to, let's write it as equal to A, where A stands for the answer. If I can figure out what A is, then I have the answer to the question. I will show you how you don't need to do that. But I've already told you, everybody, that if you have something which doesn't make sense to you, you want to find the value of A here. And I think for most people, does anybody know the value? I don't want you to tell me. So nobody does, and that's to be expected at this point. But I've told you, if you don't understand it, rewrite it the other way. So this becomes B raised to the A equals 1. And the question now is, what does the exponent on B have to be to give you 1? Has to be 0, sure. The only thing you can raise a base to get the number 1 is 0. I think, and by the way, when I do this on the calculator, there's a lot that you don't know yet about your calculator, but look up here near the top of my calculator screen where I said log of 1. There's no base there, which is what you don't understand yet. Log of 1 equals 0. And it will be 0 whether it's log base 2 of 1 or log base 11 of 1. What about something like this? Now, by the way, I said I was going to explain how you do this without saying equals A. Okay, so listen carefully. A logarithm is an exponent. Let me repeat that. A logarithm is an exponent. So this thing is an exponent. It is the exponent to which you raise b to get 1. I understand that this is essentially the same thing that we did there, but you're not actually introducing a variable. You're just saying, what exponent do I raise b to get 1? So if that works there, let me ask you this question. To what exponent, and I'm going to make this just a little bit bigger, or a lot bigger, to what exponent do you raise this b to get this b? 1. You have to raise the base b to 1 to get b. So this is equal to 1. Now, if you want, you could do this, and I hope that this is going to make sense. Log base b of b equals the answer to the question. Let's write this in exponential form. If I write it in exponential form, I will have the base raised to the other side equals what I'm taking the logarithm of, which is b. And now what we have, everybody, actually is an equation from yesterday. We have an equation that's exponential, and the base is the same, which means the exponents must be the same, which means a equals 1. That may be overkill for some of you. Let's take a look at C. C is saying, and this is a little tricky, but I want you to try. To what do I raise b? The base I've highlighted in blue. What do I raise that blue base to get b to the n? Well, n. The only way I can get b to the n is to take b and raise it to the n. So this is equal to n. Now again, if you wanted to take this approach, you could say log base b of b to the n. Oh, and by the way, I know for a fact on your handout that question C does not have brackets around b to the n. It should. It's a technicality, but sometimes I get lazy and I don't include the brackets. They should be there. Okay. You could say that this is equal to a, rewrite it in exponential form, so you take the base raised to the exponent equals what you're taking the logarithm of, and then just compare n and a, and you can see that a and n are the same, which means this logarithm is equal to n. You know, I'll be honest with you. Let me pause and go through this again. Getting the answer, so looking at what we did above this line, by simply saying, to what exponent do you raise b to get b to the n? To me, that's so much cleaner and less confusing than everything I've written below the line. It really is. But you have to find your own comfort zone. For example, this one. You have to start seeing log base 2 of 64 as being the exponent to which you raise 2 to get 64. And that's the problem right now that you're faced with. What exponent do you raise 2 to get 64? Is it 2 to the 2, 2 to the 3, 2 to the... What is it, Shazmada? I believe it's 2 to the 6. And you can confirm that on your calculator or in your head that this is 6. We did not need to write 2 raised to our answer equals 64, although you could have, and then solve this as an exponential equation. And I'm going to pause here and tell everybody that at some point you are going to learn, most of you will learn, that you can calculate these numbers on your calculator, but I do not want you doing that. Believe me, if you find a shortcut on your calculator, you are just going to fall to pieces when you get to, if you turn to page 17 of your unit handout and look at example number 3, or example number 1, you're just going to fall to pieces, because those examples don't involve numbers, they involve variables, and you can't type that into your calculator. Log base 6 of 1/36th. I am curious. I don't expect any of you to know, but how many of you feel pretty confident that you know what log base 6 of 1/36 is equal to? A few people. This is one where I would definitely recommend saying to yourself that this is the exponent to which you raise 6 to get 1/36. That's what the question is saying. To what do you raise 6 to get 1/36? How many of you, is there anybody in the room right now who now knows the answer to this that you didn't know a minute ago? Okay. And there are still going to be people in the room who still don't know. But this is an equation, bless you, from yesterday's lesson. It's an exponential equation, but you can write both sides of the equation as a common base. For example, I can write this as 6 raised to the 1 equals 1/6 raised to the 2. Well, not 6 to the 1. I'm just going to put 6 to the question mark. Let's leave it as question mark. And 6 to the 2 on the bottom can be rewritten as 6 to the -2 on the top of the fraction. So, William, for example, you had indicated you knew what it was to begin with. Does that match what you thought? And then some of you, as soon as I wrote this, I think, Marcel, you realized what it was. Does that match what you got? And the rest of us, you may have to go a little step further and show your work here by writing an exponential equation. But again, you're taking something that you do not understand, you're rewriting it into a simpler question, something we already know how to do from yesterday. Log base 8 of 2. Again, I'm just curious, how many of you know what log base 8 of 2 is equal to? Jonathan, let's just go right to the answer and then we'll explain it.
64.
It is not 64, actually. Marcel? It is 1/3. How many of you, when I say it's 1/3, now understand why it's a third? Couple nods. But you might not have understood a second ago. What we can do here is say that this that we're trying to find is the exponent to which you raise 8 to get 2. Now, again, we're always going to be at different levels of abilities here. How many of you see that it's a third because you're saying to yourself the cube root of 8 would give you 2? Some of you will be doing that. If that doesn't do it for you, this is a problem from yesterday. Solve this exponential equation. Well, you can write this as a common base of 2. So the 8 becomes 2 to the 3 raised to the x equals 2 to the 1. That means we get 2 to the 3x equals 2 to the 1. So the exponents are equal. And you have 3x equals 1. So when we divide both sides by 3, you get a third. Number 5. So if I don't write the base and I write log, it's called a common logarithm and it means base 10. So if I ask you to evaluate log of 10,000, this is log base 10 of 10,000. So I would like everybody to ponder this fairly basic puzzle. To what exponent do you raise 10 to get 10,000? So that's the first line of attack. That's what, and I don't mean to rank people, but it's a fact. That's what the top end of the class will be able to think about to get the answer. To what do I raise 10 to get 10,000? They will be able to get it. Maybe the next layer needs to actually say 10 raised to some exponent equals 10,000, which, by the way, is exactly what the top layer is thinking. But some students may need to write it down to see it. There's another group of students that have to go a little bit further and say, I'm going to write these with a common base. And I can write 10,000 as 10 to the, and it's at this point in time that everybody should clue into the fact that the answer is 4. Because 10 times 10 times 10 times 10 is 4, which means 10 raised to the 4 is 10,000. So this is equal to 4. How many of you knew it was equal to 4 as soon as I said, to what exponent do you raise 10 to get 10,000? A lot of people will. Okay. By the way, that's the key on your calculator. Log of 10,000 is 4, because 10 raised to the 4 gives you 10,000. Without using a calculator, what is this? Well, this is log base 10 of 0.001, which is log base 10 of 1 over 1,000. By a show of hands, just put your hand up and then down. How many of you know what this is equal to? Okay. If you don't, then you need to say that this is the exponent to which you raise 10 to get 1 over 1,000. And I know that when we went from just thinking about it to writing it down here, a lot of light bulbs went on in a lot of your heads. I know that not as many light bulbs will necessarily go on here in this one. But if we write this as a common base, this is 1 over 10 cubed. 1 over 10 cubed is 10 to the negative 3. So the exponent to which you raise 10 to get 0.001 is negative 3. And you can certainly check that on your calculator. Log of 0.001 gives you negative 3. Any questions with the common logarithms? Okay, the next little exercise is to get us thinking about logarithms and getting a better grasp on what they mean. What is log base 3 of 50 about? So don't forget that log base 3 of 50 is saying that we want the exponent to which you raise 3 to get 50. So how do we do this? How do we estimate this? And you would never be given an exam question like this, but it's very valuable, I believe, to do this as a group. I know it's not 2, because 3 to the 2 is not 50. 3 to the 2 is 9, right? I know it's not 3, because 3 to the 3 is 27. I know it's not 4, because 3 to the 4 is 3 times 3 times 3 times 3, which is 81. If I want to get 50, just think about this for a second. If I want to get 50, then all I can say is I need to raise 3 to a number that's between 3 and 4. That's all we can say. That this logarithm is something between 3 and 4. And so how do we write this? Let's write an answer here first of all. 3 is less than log base 3 of 50, which is less than 4. That's all we can do to estimate the value. You cannot start saying, well, if that is halfway between 27 and 81, which it isn't, then the answer will be 3.5. Logarithms don't work that way. Some of you are going to pick up on a rule here. You will not understand why the rule works, but we will learn the rule at some point. It turns out that it's actually that number, okay? And if you didn't see how I got that, that doesn't matter because I really didn't want you to see how I got it, okay? I'm claiming that that is the number to which you raise 3 to get 50. 3 raised to that number gives you exactly 50. So there will come a time where you will learn how to find that. What is log of 250? Log of 250 is log base 10 of 250, which is the exponent to which you raise 10 to get 250. Well, I know that 10 squared is 100. I know that 10 to the 3 is 1,000. So that means log base 10 of 250 has to be a number between 2 and 3. Because 10 raised to that number is going to give you 250. So we can answer this question by saying 2 is less than log 250, which is less than 3. Of course, we can check this on our calculator easily because we have a log base 10 button. It's called log. Log of 250, log of 250 is about 2.4. But that's not the point of the question. The point is to wall that log of 250 between two whole numbers. And finally, the next example, which is a whole series of different questions. What is x? So I want everybody to remember something. I'm assuming here that everybody can convert a logarithmic to an exponential equation and vice versa. Remember that I told you if you ever want to gain a deeper understanding of something, think of it in the other form or write it in the other form. So if you need to write this in exponential form, do so, but I would like you to figure out the value of x. Well, in exponential form, it's 3 to the x equals 27. And I would hope, and this may not be the case, that you don't really have to write anything else to know the answer is 3. If you want to be clinical about it and say, oh, this is an exponential equation from yesterday, I'm going to write these both with the same base, and then you're going to say the exponents are equal. If you need to do this and this, that's fine, do it. But I'm saying you probably shouldn't have to. You should probably be able to look at that and say x is 3. How many of you were able to just look at the original expression and say x is 3? It's 3 raised to the x equals 27, so x must be 3. Let's take a look at the next one. I would like you to try this one on your own, and then I will give you the solution. We're not in any big rush here. I'm just asking because I think it's helpful for me as your teacher to know. How many of you looked at this and thought about it for a few seconds and said, I know what the answer is? Good. 1/3, right? How many of you looked at it and said the answer is 1/3 because the base of 27 needs to be cube rooted to get 3? On the other hand, there is going to be a group of people, and this is definitely a case where some of you need to do this. That's not an unexpected thing. I would expect that there are going to be students that need to actually rewrite this in exponential form, say it's a common base situation. This is why we did yesterday's lesson before we did this. So I can write 27 as 3 cubed. This is raised to the x. This is equal to 3 to the 1. I have a power of a power, which is found by multiplying these two exponents to get 3 to the 3x. And that means the exponents of 3x and 1 are equal. So when you divide both sides by 3, you get x equals a third. And you know, if it were a written response, I think this is a pretty piddly written response question. I don't think you would see it, but if it were, you really should show those steps. Even though, I don't think it would be because it's too obvious for many of us. I would like everybody to see if you can figure out what x is here. And again, what you're doing in all these cases is you're thinking in the other language. You're saying, well, there's a logarithm. Let me think about what it means exponentially. Hand up and down if you have it. And I'm assuming those people had it almost immediately. And I would say that those people who have it almost immediately have it immediately because they know their powers. They know, you know, powers of 2, powers of 3, powers of 4, etc. How many of you got 3 because you know that 3 to the 4 is 81? Okay. When I rewrite it this way, though, how can we solve it algebraically without having that knowledge? Because what if it's, I mean, let's face it. What if we had b to the 40 equals 1.8, which we're going to. You're going to see stuff like this. You can't tell me that in the deep, dark recesses of your brain, you know what number raised to the 40 gives you 1.8. That's impossible. So did anybody get 3 on the left-hand equation by actually algebraically doing something? Yes? What'd you do?
I raised 81 by 1/4.
Excellent. And that's what I would like everybody to do. There's another thing you could do, but I'm glad you said this. I'm going to raise both sides of this equation to a quarter. Because now on the left I have x to the 4 to the quarter, and when I multiply those two exponents, I get x to the 1. So it's 81 to the quarter. In your mind, Shesmaida, do you understand that's the 4th root? Okay, that's the other way to go, is to say, if I have x to the 4 equals 81, I'm going to take the 4th root. The problem is, well, there's a number of problems with doing that. You'll get the same answer. Navigating to a 4th root on your calculator is a little clunky, and sometimes it's not a whole number. So the concept of a root kind of breaks down. I think this is the best way to go. And then you can take 81 raised to the quarter on your calculator. Of course, when you do that, you either have to put 1 divided by 4 in brackets or raise it to the 0.25. D, I would like everybody to figure out what x is. The only thing that this really requires is that you can see that in exponential form or write that in exponential form. So how many of you got 125 without actually writing anything else down? You just maybe used your calculator or your head. If you have to take that preliminary step of writing 5 to the 3 equals x, and then that light bulb goes on in your head where you go, oh, x is 5 to the 3. I'm going to figure out what 5 to the 3 is. That's fine too. But this is 125. X equals 125. And it just occurs to me if I go back here, I didn't write x equals 3. I did write x equals a third. and e log base 1/2 of 32. There's probably brackets around your half in your handout. I just didn't feel like trying to format it on this file. What's a tougher one? I'd like to see if you can figure it out on your own first. Well, I think it's tougher, but I'm seeing most of you just looking at me as if the answer was obvious. To how many of you is the answer obvious? Or not obvious, you're pretty sure you know. You take a crack, Madison? -5 is right. And this is a weird thing. How many of you you're pretty sure it's -5, and it is, but maybe you're not quite sure why. It just kind of in the back of your brain, you kind of go, well, I'm pretty sure it's going to be -5. And it has to do with that 1/2. If that 1/2 were just a 2, this is an interesting property of logarithms. If that 1/2 were just a 2, I'm going to call it y, because it's different. The answer is 5, right? 2 to the 5 is 32. If you flip the base over, you change the sign on the logarithm. There's a kind of a neat little rule there. Anyway, this is -5 because if we write 1/2 raised to the x equals 32, we can write 1/2 as base 2, 2 to the -1, and it's raised to the x. We can write 32 as base 2. On the left side, we have a power of a power, which gives us 2 to the -x. When we multiply those exponents, equals 2 to the 5. That means -x equals 5. I don't know, switch the sides, multiply both sides by -1. Lots of ways you can see that x is -5. Is that the final example?